Logarithms, exponentials, solving equations. What are they? Logarithms. How many of this number do we multiply to get that number using powers? Why? Helps to measure the amount of molecules. Interesting fact, guinea pigs can swim, but they don't usually enjoy it. Now, let's take a look at the definition of a logarithm. So we have, let a be a positive real number different from 1. The logarithm of x with base a is y is equal to log of x with base a if and only if x is equal to a raised to the y, for every x greater than 0, and for every real number y. Let's look at the conversion chart of logarithms to exponentials and vice versa. The key elements are the bases are the same, and the output of the logarithm is the input of the exponential. The other key part is for every x greater than 0. That means the input of a logarithm must be positive. Now, let's take a look at the examples we're going to discuss in today's video. Let's take a closer look at example 1. Now, let's read the steps. Step 1. Are the bases the same? Step 2. Remember to switch functions. Step 3. Set inputs equal if multiple terms. Step 4. Solve and verify. Now, let's read the question. Solve the equation where we have the log of 2x minus 3 with base 3 is equal to 4. Let's write down the equation so we can show our work. Let's convert this logarithm to exponential so we can better solve for x. So now we have 2x minus 3 is equal to 3 to the 4. We follow the conversion chart. So the base of the log, 3 in this case, becomes the base of the output, which is 4 in this case. And we set that 3 to the 4 equal to what is inside the parentheses, 2x minus 3, or the input of the log. Let's multiply. So 3 to the 4 becomes 81. So now we have 2x minus 3 is equal to 81. Let's add 3 to both sides, and 81 plus 3 is 84. So now we have 2x is equal to 84. Let's divide both sides by 2, and our result is x is equal to 42. Remember the second key bit that we talked about with the definition of a log? That the input must be positive? Well, now we have to verify. So let's substitute 42 for each x into the original equation. So now we have the log of 2 times 42 minus 3 with base 3 is equal to 4. Let's multiply. And 2 times 42 is 84. And 84 minus 3 is 81. So now we have the log of 81 with base 3 is equal to 4. Let's use the conversion chart to convert this logarithm to an exponential. So now we have 3 to the 4 is equal to 81. And 3 to the 4 is 81. So now we have 81 is equal to 81. Since that is true, our answer, x is equal to 42, works. And that is example 1. Let's move on to example 2. Now, let's read the question. Solve the equation where we have the log of x minus 2 with base 7 is equal to the log of 4x minus 5 with base 7. Let's write down the equation so we can show our work. This time, since we only have log with base 7 on each side, we can drop the logs and only worry about the inputs, since the output will be the same. So now we have x minus 2 is equal to 4x minus 5. Let's add 2 to both sides, and negative 5 plus 2 is negative 3. So now we have x minus 4x is equal to negative 3. Whoa! What other step do you think we did at the same time? That is correct. We subtracted 4x on both sides. Now, let's combine the like terms on the left side, and our result is negative 3x is equal to negative 3. Let's divide both sides by negative 3, and our result is x is equal to 1. Remember that second key bit that we talked about with the definition of a log? That the input must be positive? Well, now we have to verify. So let's substitute 1 for each x. So now we have the log of 1 minus 2 with base 7 is equal to the log of 4 times 1 minus 5 with base 7. Now, let's simplify. 1 minus 2 is negative 1, and 4 times 1 is 4. Let's simplify a bit more, and 4 minus 5 is negative 1. So now we have the log of negative 1 with base 7 is equal to the log of negative 1 with base 7. Ew, what do we think this means? That is correct, no solution, because the input is negative, which means x is equal to 1 does not work. That is example 2. Let's move on to example 3. Now, let's read the question. Solve the equation where we have e raised to the 2 times the natural log of 4x plus 1 is equal to 9. Let's write down the equation so we can show our work. Let's use the power rule to move that 2 in front of the natural log back to a power. So now we have e raised to the natural log of 4x plus 1 squared is equal to 9. Luckily for us, e and the natural log are inverses, so they cancel out. So now we have the quantity of 4x plus 1 squared is equal to 9. Now, we could distribute the two binomials by using the FOIL method, but since both sides are perfect squares, let's take the square root on both sides. So now we have 4x plus 1 is equal to plus or minus 3. Let's separate the one equation into two. So now we have 4x plus 1 is equal to 3 and 4x plus 1 is equal to negative 3. Let's start with 4x plus 1 is equal to 3. Let's subtract 1 on both sides, and 3 minus 1 is 2. So now we have 4x is equal to 2. Let's divide both sides by 4. So x is equal to 1 over 2, because 2 over 4 simplifies to 1 over 2. Let's continue with 4x plus 1 is equal to negative 3. Let's subtract 1 on both sides, and negative 3 minus 1 is negative 4. So now we have 4x is equal to negative 4. Let's divide both sides by 4, and our result is x is equal to negative 1. Remember that second key bit that we talked about with the definition of a log? That the input must be positive? Well, now we have to verify. So let's substitute 1 over 2 and negative 1 into the original equation. Let's start with e raised to the 2 times the natural log of 4 times 1/2 plus 1 is equal to 9. Let's simplify. And 4 times 1/2 is 2, and 2 plus 1 is 3. Now, let's use the power rule, and 3 squared is 9, and e and the natural log cancel, so we're left with 9 is equal to 9, which is true. Let's continue with e raised to the 2 times the natural log of 4 times negative 1 plus 1 is equal to 9. Let's simplify. 4 times negative 1 is negative 4, and negative 4 plus 1 is negative 3. Now, let's use the power rule, and negative 3 squared is 9. And the e and natural log cancel, so we're left with 9 is equal to 9. Which is true, but we made a mistake somewhere, so it is important not to go too fast. So do you think we can do this step? That is correct, we could not, because the input of a log or natural log must be positive. So we could have stopped here, since the input is negative, which means x equals negative 1 does not work, so only x equals 1/2 works. That is example 3. Now it is your turn, so go ahead and pause the video here so you can take your time to answer this question, and I'll show you the result in 3, 2, and 1. Did you get it correct? Awesome. If not, there's always tomorrow.